The difference between the initial and the final position of an object. Displacement. Displacement is how far out of place an object is. It's the shortest path from start to finish.
Imagine trying to find your way back to your parked car after shopping at a large mall. This situation is similar to the concept of displacement, where you need to determine the straight-line distance from the store you ended up in to your car, not the winding path you took to get there. Just as finding your car involves knowing where you started, your car's location, and where you ended, the store. Displacement measures the direct distance between an object's initial and final positions, regardless of the journey in between.
A place or object used to describe the position or motion of another object. Reference point. In science, a reference point is a fixed place used to determine if something else is moving.
Imagine you're trying to meet a friend in a crowded park, but neither of you knows exactly where the other is. You decide to use a large, distinct statue in the park as your meeting point, which helps you both describe your position relative to it and allows you to find each other more easily. In science, a reference point functions similarly by providing a fixed location or object to determine the position or motion of other objects. Much like the statue helps you and your friend establish your locations in relation to each other. Just as the statue serves as a common point for both parties to describe their movements and positions, a reference point in physics helps define where and how objects move or are positioned.
If the net force acting on an object is zero, the motion of the object does not change. Newton's first law of motion. Objects keep doing what they're doing unless something makes them change.
Imagine you're sitting on a couch, perfectly relaxed, and you don't want to move unless something or someone forces you to. This is similar to Newton's first law of motion, which states that an object will stay at rest or keep moving at a constant speed in a straight line unless acted upon by a net external force. Just like you won't budge from your comfy spot without a nudge or motivation. An object won't change its state of motion unless an unbalanced force, like a push or pull, acts on it.
The acceleration of an object is the net force exerted on it divided by its mass. Newton's second law of motion. Simply put, this law explains that how fast something speeds up depends on how hard you push it and how heavy it is.
Imagine you're trying to push a heavy shopping cart through a crowded supermarket. The difficulty you experience is similar to Newton's second law of motion, where the effort or force you apply to move the cart needs to overcome both the cart's weight, its mass, and the resistance from the crowd, like friction. Just as the cart accelerates more easily when you push harder or when it's lighter, an object's acceleration is determined by the net force you apply to it, divided by its mass, emphasizing how both force and mass influence movement.
For every action, there is an equal and opposite reaction. Newton's third law of motion. When one object exerts a force on another, the second object exerts an equal and opposite force back.
Imagine you're trying to push a heavy piece of furniture across your living room floor. When you apply force to push the furniture, you might notice that your feet are simultaneously pushed back by the floor. This is similar to Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. In this analogy, the action is the force you exert on the furniture, and the reaction is the equal force the floor exerts on your feet, illustrating how forces always come in pairs, just like trying to move something heavy but ending up moving yourself slightly instead.
A quantity with both a size and direction physics. Vector. In simple terms, a vector is an arrow that shows how much and which way something is moving or acting.
Imagine trying to navigate your way through a crowded shopping mall to find a specific store. This situation is like a vector in physics because just knowing the mall's size or the distance you need to cover isn't enough. you also need to know the direction to head towards your destination. Similarly, in physics, a vector is a quantity that has both magnitude, the size or distance you need to cover, and direction, the path you need to take. Just like you need both pieces of information to successfully reach the store in the mall.
A change in velocity with respect to time. Acceleration. Acceleration is how quickly something speeds up, slows down, or changes direction.
Imagine you're driving on a highway and suddenly realize you're late for a meeting, so you need to speed up. This situation is similar to the scientific concept of acceleration, which is a change in velocity with respect to time. Just as you press the gas pedal to increase your speed, change in velocity to catch up to your schedule over time. An object accelerates when its velocity changes over time, whether that's speeding up, slowing down, or changing direction.
The distance an object travels divided by total time taken. Average speed. It tells you how fast something is moving overall during a period of time.
Imagine you're trying to figure out how much money you spend on groceries each month. Just like you calculate your monthly grocery expenses by adding up all your receipts and dividing by the number of weeks, average speed is found by dividing the total distance traveled by the total time taken. In both cases, you're determining a rate. For groceries, it's your spending per week, and for speed, it's the distance per unit of time.
The rate of change of position, in which the same distance is traveled each second constant speed. Constant speed means you are moving at the same pace without speeding up or slowing down.
Imagine you're baking cookies, and you have to roll out the dough to an even thickness across the entire sheet. Just like ensuring the dough is the same thickness everywhere, constant speed means traveling the same distance every second. In both cases, for cookies, every part of the dough is evenly rolled out, and for constant speed, every second covers an equal stretch of road, ensuring uniformity and consistency in both tasks.
An object's speed at an instant of time. Instantaneous speed. Instantaneous speed is how fast something is moving at a specific moment.
Imagine you're trying to find the exact moment your toast pops up from the toaster so you can catch it perfectly. Just like waiting for that precise instant when the toast is done, instantaneous speed is about capturing an object's speed at a specific moment in time. In this analogy, the toaster's timer represents an object's journey, and catching the toast at the right moment is like measuring the object's speed at an exact point, without considering what happened before or after.
The distance an object travels per unit of time. Speed. Speed is how fast something is moving.
Imagine you're trying to manage your budget by tracking how much money you spend each day. Just like keeping an eye on your daily expenses gives you an idea of your spending habits, measuring the distance an object travels in a specific time frame tells you its speed. In this analogy, your daily expenses represent the distance, the days are the time, and your overall spending pattern is like the speed, providing a clear picture of how fast your finances are moving.
Speed and direction of a moving object. Velocity. Velocity is how fast an object is moving and in which direction.
Imagine trying to reach a friend's house in an unfamiliar neighborhood without a GPS. Just like you need both speed and the correct direction to arrive at your friend's house efficiently, velocity provides both the speed and direction needed for a moving object to reach a destination. In this analogy, the speed of your car is like the speed component of velocity, while knowing which roads to take represents the direction component, both of which are crucial to successfully reaching your endpoint, just as velocity is essential for predicting where and how quickly an object will move.
The steepness of a line on a graph equals vertical change over horizontal change. Slope is a measure of how steep a line is on a graph, indicating how much the line goes up or down for each step it goes across.
Imagine you're riding a bicycle up a hill and you're trying to figure out how challenging the climb will be. This is similar to understanding the slope of a line on a graph, where the steepness of the hill represents the vertical change, and the distance you travel horizontally represents the horizontal change. Just like how the effort required to pedal up the hill depends on how steep it is, how much you rise for every bit you move forward. The slope of a line is calculated by dividing the vertical change by the horizontal change, helping you grasp how steep or flat a line is on a graph.